Okay, short preface to the intro after I shot the video. Yeah, it will be quite a journey until we arrive at that picture. And that picture has its caveats, so curb your expectations. What we will get is pretty much a real-time Bode plot, at least for the amplitude response, frequency response of a circuit. At the very end I come up with the amplifier. If you don't want to go through the whole video, just use the time index below and go to the summary for the VCO setup. That's basically all you need to get that curve. Okay? Enjoy! Welcome to this little tutorial about creating a poor man's Bode plot that is measuring the frequency response of some circuit, that one here in this case, with an El Cheapo function generator, in this case the FEEL-ELEC or FEEL-TEG FY6800, which is electrically I think the same as their newer model, the FY6900. The newer one has just a nicer case and an oscilloscope without any special provisions for creating Bode plots. And no, it's not possible to create real Bode plots with that equipment, but at least we should get some meaningful curves here on the oscilloscope. Hopefully, we'll see. This video was brought on by some user comments. There was one comment on my FEEL-TEG FY6800 review card link by René Jean Mercier. I hope I didn't butcher that name. And he basically wants to frequency sweep an amplifier, and he has a problem to synchronize the sweep signal from that FY6800 with the scope, so you get a steady signal on the scope. And there was a second comment from 7 months ago. That was a lengthy discussion. There's more down here with Nemo regarding the addendum to the FY6800 review, also card link. He basically had the same idea. Okay, you need a sweep frequency signal for an oscilloscope, and would it be possible to generate some sync signal using the second channel of the device? And my first basic idea was, okay, maybe you can use the VCO functionality, and but again, I made no promises of trying it, but he really dove deep into it. So that thread continued for a while, and he did some extensive research by himself, and he found some evidence, I will put that link down below too, that the VCO in the FY6800 is not working in a linear fashion. That is, the frequency does not increase linearly when you increase the voltage in the VCO input. But as a last resort, he found something, link again, found something, link again, I will put it down below, that it might work using frequency modulation mode. And the discussion continues, and I didn't promise, no promises, that at one point I will try that, and we are at that point now. So what is this all about? Bode plots, frequency response of some circuit Let me scribble down very quickly what I have here on the bench right now. I have my signal generator that's generating a sine wave on channel 1, which goes via a coax cable to my breadboard, and is of course terminated by not 50 ohms but 51 ohms, near enough, and that is fed into an RC low path. And the scope is simply measuring what goes into this RC low path on channel 1 and what's coming out of this RC low path on channel 2. So, and the RC low path we are measuring here is also called, in general, the DUT, the device under test. This doesn't have to be an RC low path, of course. This could be any circuit, including, for example, something active like an amplifier. That was the questions of René Jean. So let's get back to the scope and play a little bit. So I'm currently at 2.3 kilohertz, and if I decrease the frequency, you see something happens. Yellow is channel 1, so my input, and blue is channel 2, so my output from the RC filter. And let me change the time scale a bit. If I decrease the frequency further, you see our output signal gains in magnitude, and the phase shift between the input and output signal gets smaller and smaller. Okay, and if I increase that, say, to 5 kilohertz or something, let me correct the scale. You see our output is now really low, and we have an almost, 90-degree phase shift here. And that frequency response of, in my case, an RC low path, but of any device under test, you can visualize with a Bode plot. It's not a nice Bode plot. I've drawn it. So basically you have down here the frequency, which is usually in a logarithmic scale. And you have the magnitude of the output signal. In a passive circuit, this is the top value is 0, and then you only have negative decibels. In an amplifier, you can, of course, have positive decibel values. It's usually in decibel. It doesn't have to be in decibel. And on the other side, you have the phase shift. So what we've seen here, my RC low pass has some frequency it's operating on. And if I increase the frequency, my magnitude at one point starts to drop. Okay, and the frequency of the RC low pass, you know, that is when we reach minus 3 dBs or 70.7% or 0.707 of the magnitude of the input signal. At the same time, we are now here at that scale. We have a phase shift that changes while we change the frequency. And for RC low path, at the beginning, at low frequencies, the phase shift is 0, and then it increases until we reach the frequency of the low path. At that point, it should be ideally minus 45 degrees. And then, it continues to increase until we reach, ideally, minus 90 degrees. And because sweeping through the frequency manually, while I may be changing something in my circuit, here is a little bit So yeah, naturally, most of these generators have something like a frequency sweep, and I will set up now a frequency sweep. And I set up here a frequency sweep on the signal generator, yeah, with a sweep button. So my start frequency is 20 Hertz. My end frequency is 20 kilohertz. And I do the sweep in 0.1 seconds. And on the oscilloscope, you see some funny things are going on, of course. But if I press stop, and my sample length is 40 megasamples, and I, squish the time scale together, we get this thing is not working perfectly, but we get, at least in the amplitude, and that's what we will aim for in this video, we get the frequency response curve. Obviously, it's far from perfect. The reason being, that thing is not really synced to this thing here. So the goal here is to get out of our generator a frequency sweep signal, so a sine wave with increasing frequency. We will get a sine wave out here with, in our case, RC low path, decreasing amplitude and increasing phase shift in relation to the input. But I won't really, can't, or have no idea how to do anything about measuring the phase automatically. And both things go into our oscilloscope, and we won't get a real Bode plot like that one. But we will be happy if we have something like this here. Something that at least indicates how the magnitude of the output signal develops in the frequency band we are feeding in here. And I should mention at this point, there are of course special devices that make such Bode plots, and at least I know Sigland has oscilloscope that communicate over USB with a Sigland signal generator. So the oscilloscope has a special Bode plot mode and tells the generator which frequency to generate while it's plotting the frequency response of the DUT. And there are a whole lot of expensive, that's the problem, expensive solutions to create real Bode plots. But we really want to do it with, just for the amplitude response, with the El Cheapo setup I have here on my desk. Okay, the scope is not that cheap, but the function generator is. So the first step would be, or the first approach, my initial approach, to use the VCO functionality of that thing instead of an automatic sweep. And you remember in the comments somebody found out that the VCO is not really working in a linear fashion dependent on the input voltage. But let's verify that first. So right out of the bat, I set up the VCO here, and I connected at the VCO input at the back a coax cable, and I shorted it out to be sure I'm on 0 volts. And my start frequency, I will zoom in later maybe, is 1 kilohertz. And the thing outputs 1.26 kilohertz. I still have shorted the VCO input of the function generator, and I changed the start frequency to 20 hertz. And I'm getting out 290, 300 hertz. So right off the bat, we obviously have here an undesirable offset of the frequency of about something between 250 and 300 Hertz. And these are the settings I'm using. So VCO and object is frequency. We are sweeping, not sweeping, VCOing. Start frequency 20 Hertz, end frequency 20 kilohertz. Mode is linear, in relation to the input voltage, or should be. And we go forth, not back. Let me experiment a little bit. If I start the sweep from the back, again, I have 19.7 kilohertz instead of 20 kilohertz. So, 19.72. So again, 280 hertz offset. And that doesn't get better if I switch the mode to logarithmic. That is logarithmic frequency increase or decrease in the, on the input voltage. Now I start, if I go backwards from the highest frequency to the lowest at 0 volt at about 19 kilohertz. And if I go from the lowest frequency up, I start at 1 kilohertz. So the VCO input is not very accurate. I don't know if this is in the analog part some offset voltages, or if the reference of the analog to digital converter, which must be in here somewhere for the VCO input, the reference is off. I really don't know, but we need to keep that in mind, that even the start and the stop frequency are not necessarily those which we set in the device. And another tidbit of information, the input resistance of the VCO input at the back is 26 kilo ohms, so not really high impedance, but also not 50 ohm terminated. So what I'm doing now is I'm feeding the VCO input via a little voltage divider here, a defined voltage from my power source, which I display here, and I will write down the output frequency at each voltage. And for 0 volts we have let's say 300 hertz. Okay, for 1 volt we have 4 kilohertz. For 2 volts I read 7.8 kilohertz. For 3 volts 11.5 kilohertz. 4 volts 15.3 kilohertz. 5 volts 19 kilohertz. And just because I want to know when we hit actually 20 kilohertz, I will go a little bit beyond the 5 volts. Maybe I kill the input of the unit, but Okay, at 5.26 volts, 20 kilohertz. Let me tune this down and reverse the polarity here. Please note this voltage is now negative in the VCO input. So I want to see if I can go down to 20 hertz with a negative input voltage. Yep. So at minus 85 millivolts I have 20 hertz. If you look at the measurements I took and the delta, frequency delta between each voltage step, you see the VCO is behaving, in fact, in a linear fashion. So delta 3738, 3738, 37 kilohertz. That's within measurement errors, I guess, linear. The problem is, of course, that our set lower and set upper frequency is not reached between 0 and 5 volts. But we can maybe we are able to make accommodations for that. Let's see. So I turned down, yeah, you probably can read it, you have to believe me. I turned down the start frequency here to 1 Hertz, and we are still at these almost 300 Hertz here at 0 volt input voltage to the VCO. So yeah, turning down the start frequency here on the unit itself doesn't work. We will need a negative VCO frequency to get down to my 20 Hertz I want. However, I was able to make a suitable correction on the unit for 5 volt input voltage to the VCO, and my end frequency, yeah, I give you a close-up in a second, at 21 kilohertz, I get out 20 kilohertz. These are my final VCO settings. So object which we are varying by voltage is the frequency. My start frequency is 20 Hertz. My end frequency is 21 kilohertz. My mode is linear, direction is fourth, so from start to end frequency with increasing voltage. That's it. Side note, the guy who said that the VCO is not working in a linear fashion might have, that's just one idea, one possibility, have the mode wrong, because there is a logarithmic mode, a linear mode and a logarithmic mode. Or he has a unit with another firmware, or yeah, or I don't know. Anyway, with these settings, I can coax the VCO in here to give me a frequency between 20 and 20 kilohertz with an input voltage of minus 0.085 volts and 5 volts. Now that we characterized our VCO and set it to suitable parameters, we need a ramp signal, and we start with a linear ramp here to feed into the VCO input to automate, yeah, to get our frequency sweep. And there's where the next problems arise. I feed the signal into the scope on channel 3 without any termination. The problem I ran into, if I put a 50 ohm termination at the input of the oscilloscope, I didn't get a linear curve anymore. At least not for the voltage range I need, and that is, well, 0 to 5 volts. So I run this now without termination, which should be okay, because we are running that only at 7 Hertz. Yeah, 7 Hertz, that was the combination where I got the most usage on the ramp out of my oscilloscope screen. And I fine-tuned on the oscilloscope the voltage levels. So we have 5 volts here at the top cursor line, and we have 0.8 volts at the lower cursor line. And you see, yeah, it's making little peaks here. That's, well, it's a cheap function generator. And these are my settings for channel 2. So frequency, ramp of course, and frequency 7 Hertz. My amplitude is 5.1 volts. And yeah, forget about all this decimal precision stuff here. It doesn't really work. And offset 0.244 volts. Yeah. Okay, let's feed that signal now from channel 2, not only into the oscilloscope, but also into the VCO input at the back. And indeed, we get something like a frequency response curve here. Let me zoom in. So our input sine wave becomes mostly, but yeah, here for the very low frequency stuff, around 20 hertz. I mean, this is 7 hertz signal here on my VCO becomes simply a colored area. Yeah, the sine wave lines are all overlapping, and the same is true mostly, but for the low frequency stuff here, for the output signal from my DUT. So yeah, doesn't look like a Bode plot, that curve here yet, and there's a reason for that. You remember the Bode plot usually has a logarithmic scale for the frequency, and at the moment we are doing only a linear scale down here, so we don't see, for my example, the RC low path, this nice curve here with the knee. So let's try if we can get the VCO to do something logarithmic. Okay, that has no longer any meaning because we are using not the power supply but the channel 2 to feed the VCO. And within the VCO, I will zoom in a second, we can switch the mode between linear and logarithmic. Ha! Maybe that's the solution, and you probably already know. Okay, I go on logarithmic, and yeah, it's the wrong logarithmic logarithm. So I have no idea. I would have now expected something like that, but it goes even steeper. So yeah, the logarithmic mode of the VCO, going back to linear, no, obviously not. And that's the setting on the signal generator, linear or other mode, logarithmic. But as I said before, it doesn't really do what you expected. That's as close as I can get to a magnitude only Bode plot with that FY6800 function generator. So that's our input signal to the VCO, which is now an exponential curve, which it should be when we want a logarithmic frequency scale at the bottom. And it's down to 3.5 hertz, I think. That's the lowest I can get without losing my trigger. And we have our output signal in blue from our DUT, that is our RC low path. And you see, yeah, it's almost linear here in that region. I mean, the Bode plot I saw you is of course idealized. A real RC filter is not that nice. So yeah, that's, see, lost there my sync for a moment. And yellow, of course, the input signal. And yeah, works somehow. Let's have a look at the settings. So VCO is unchanged. Okay, we are changing the frequency 20 hertz to 21 kilohertz, linear and fourth. So from start to end, we already had that, it's running. And my channel 2 is now set to an n-fold exponential curve with a frequency of 3.5 hertz, amplitude 5.1 volts, and offset 2.44 volts. And I calibrated these values using the cursor functionality, voltage cursors on my oscilloscope, okay? I didn't rely on what was displayed here. And remember, I wasn't able to get a nice linear curve, a nice linear curve out of that thing when I actually terminated the output of the VCO, the output of channel 2 with a 50 ohm resistor. And that's the whole setup. The signal generator, giving out my control signal for the VCO, currently that exponential signal via 50 ohm BNC, and a T connector to the VCO in at the back of the signal generator, and then via 15 ohm BNC again into the third channel of my scope, and I'm syncing my scope of the third channel. No termination here for the BNC cable, which should be okay at 3.5 or what was it before, 7 Hertz. And don't forget to set your probe settings for that channel to 1x, okay? So the VCO output signal on channel 1 from the signal generator goes to my DUT via 50 ohm BNC and is properly terminated with a 51 ohm resistor. And the VCO signal also goes directly via 10x oscilloscope probe into my channel 1, just for reference. And the output of my DUT is also going via a 10x probe to channel 2 of my oscilloscope. The good news is we managed to sync the frequency sweep done with our function generator using a VCO with our oscilloscope, and we get out some live Bode plot like curve, at least the amplitude curve. And we were able to do this right now in a logarithmic frequency scale at the bottom, and we were also able to do it in a linear frequency scale at the bottom. And we get, a nice, usable picture qualitative wise. I mean, you can clearly see it's an RC low path, okay? But really doing some measurements with that in regards to, exact cutoff frequency and stuff, not so much. Okay, back to square one. Instead of using the VCO in here, we will now use the frequency modulation to achieve the same and see if the frequency modulation, as some people say, links below and stuff, the discussions, is actually really working better. This will go a lot faster because you will see in the end there's not a whole lot of difference between using the VCO and the frequency modulation of that thing. So we are in the modulation menu, and as mode I picked frequency modulation. At source we have again the external VCO in at the back, so we don't even have to change our wiring. At bias I have 20 kilohertz. So in theory, the output frequency should modulate plus minus 10 kilohertz, half of that, when we go from 0 to 5 volts in our VCO input. And there's also the channel 1 frequency here, which is 10 kilohertz. So our center frequency of our frequency modulation. And now let's do some measurements. So again, I'm feeding my VCO input here from my lab power supply with the little voltage divider here. Voltage is displayed here in more accuracy. Voltage divider for more control. And at 0 volts, I'm reading 200 70 Hertz. And at 1 volt, I'm reading 4.4 kilohertz. 2 volts, 8.1 kilohertz. 3 volts, 11 point whatever, 8 kilohertz. 4 volts, 15.6 kilohertz. And 5 volts, finally, 19 kilohertz. And yeah, I would have to increase the voltage further to even reach 20 kilohertz. 20 kilohertz I will reach at 5 point, let's say 2.8 volts, no, 2.9 volts. Okay, I have 20 kilohertz. And now I need to, reverse the voltage here. And let's see if we can get down to 20 Hertz with a negative input voltage. Yeah, about minus 0.77 volts. We have 20 Hertz. Let me do a little number crunching. Okay, I tried using the data I took to fine-tune the frequency modulation settings here, so we get a nice 20 Hertz to at least 20 kilohertz between 0 or a little bit negative and 5 volts, but you will get up totally screwing up the output of the generator. So I will take the initial settings, which should work, and well, we'll just cutting it short at 19 kilohertz at the top, and yeah. So here are the numbers again for frequency modulation. Yeah, my 1 volt steps and the delta between them. And if anything, this is less linear. Yeah, the talk was the VCO is not linear, but the frequency modulation stuff, at least at the extremes I'm using it, is obviously, I can put the VCO numbers for comparison. The frequency modulation stuff is less linear at the start and the end than the VCO stuff. And interestingly, to get to my 20 kilohertz with ideal settings, I needed to apply here 5.289 volts and here 5.26 volts. To get really down to 20 hertz, I have to apply here minus 0.77 volts and here minus 0.05. Sorry, forgot a 0 here. So but you get the idea. That VCO input is, which is used for frequency modulation, and the VCO is fuckered. Sorry. And let's try to get a picture with the VCO at least, so we have accomplished something. But right now I wouldn't go with frequency modulation. I would clearly go with the VCO. The rest of the setup is exactly the same as for the VCO, only, the only difference really is I changed here the thing to frequency modulation. Looks not exactly the same. I think the frequency modulation is, there are some artifacts here. They weren't here when we used the VCO, so not as nice. And again, I'm using the modulation menu. I'm using the mode frequency modulation. Our source is external VCO in. Our bias is 20 kilohertz, which only lifts us up to 19 kilohertz at 5 volts. And yeah, our channel 1, our center frequency is 10 kilohertz. And as mentioned before, the test setup is exactly the same as for the VCO. So also the wiring between the signal generator and the scope. So our poor man's Bode plot here, it's possible to do with frequency modulation, but I don't see any reason why you would do it. I mean, it's not as linear as the VCO, or whatever they tell in the, on these boards, at least not for my unit and my firmware version. I'll give you a shot of the firmware version in a second. Yeah, and the tuning of the parameter to have really exactly your 20 Hz start frequency and your 20 kilohertz end frequency, it's a pain. It's a pain using in frequency modulation mode because it's simply a pain. Forget about it. Yeah, and I'm at version 171 with my unit. Let's have some fun. I have a new DUT here, and yeah, I won't go through the cabling, but it's basically the same, yeah, DUT, only my DUT is now a 30-year-old amplifier, 30 plus year, yeah, from my youth. You have simply to appreciate that nice wood case and the labeling of the well, not hi-fi connectors and oh yeah. Anyway, what I wanted to show you is what that 20 to 20 kilohertz sweep sounds like, and it sounds like that. And I had some filters built in here too, so let's focus on our Bode plot here. And you see that amplifier, it dips in here a little, okay? And now I'm switching to another filter. Oh, that's obviously a high pass. And now you see why, even if this is only qualitative, it comes nicely when, fooling around, comes in nicely when fooling around with, some circuitry. And I'm doing audio frequencies now. You can use higher frequencies. There should be more filters in here. Low pass. Okay. Do I have something else? Another low pass? Okay. Switching. Okay, that's not connected. So I'm pretty sure there was a band path in there, but this looks like a low path to me. The next setting. This also looks like a low path. Oh, maybe the odd capacitor electrolytic dried out here. But yeah. The high pass is working perfectly, and yeah. No filter at all. You immediately recognize that because the amplitude goes up. These will be only very, very cheap RC filters in that box. yeah, just, sorry, just having fun. I know, the video is getting too long. But you see the value of an interactive Bode plot on the scope with a function generator. Okay, I guess we are at the end now. If such a near real-time Bode plot, yeah, amplitude only and qualitative only, so no exact measurements here, is usable to you, then I would recommend to go the route via the VCO. Yeah, any rumors about it being not linear are highly overrated or exaggerated is the word, I think. And yeah, I mean, creating these pictures is quite fun. So yeah, go with it. And yeah, until next time, bye.